Hello, everybody. I hope you're all in good health and also your loved ones. First of all, I would like to thank the organizing committee of ISyDMA 2020 for inviting me to give this presentation about spectroscopic investigation of hydrogenated amorphous silicon PIN solar cells. I am Professor Outzourhit from Qadi Ayyad University in Marrakesh, Morocco. Before I start, I would like to give you a brief overview of the main points of the presentation. I would like to start with the outline. So we'll start first of all by describing the solar cell configuration that we developed in this study, and also the thin film deposition techniques that we used. In addition, I will give you some results obtained by Raman spectroscopy and also ellipsometry on the films that were fabricated. In addition, of course, the solar cell parameters that were obtained, and also I'll finish by giving you some results of the measurements that were conducted using capacitance, conductance versus voltage, as well as impedance spectroscopy. Okay. The main objectives of this study are twofold. The first objective is the fabrication of high-quality hydrogenated amorphous silicon-based thin films for solar cells in either single junction forms or heterojunctions of crystalline silicon and amorphous silicon, or double and triple junctions based on silicon, amorphous silicon thin films. In addition, we would like to use a battery of spectroscopic techniques to optimize the quality of the thin films and also the performances of the devices. Okay, so the solar cell configuration that was developed is a single junction PIN type solar cells. It's in the superstrate type configuration, where the glass substrate is used as a supporting structure of the cell, as well as a window for elimination of the cell. So the cell is basically composed of an FTO coated glass substrate on which a P-type hydrogenated amorphous silicon carbide thin film was deposited with a thickness of about 12 nanometers. This P-type film acts both as a window layer and also as a carrier selective layer, because it only allows holes to pass through. This layer is followed by an intrinsic hydrogenated amorphous silicon film of about 260 nanometers thickness, which is the active layer where the photogeneration of carriers take place. This is followed by an N-type layer consisting of hydrogenated amorphous silicon N-type layer of about 20 nanometers, which is also in this case a carrier selective layer, which only allows the passage of electrons. Finally, this is completed by an aluminum ohmic contact or back contact, which acts also as a reflector that aids in trapping the light by reflection in the cells, thus maximizing the absorption of the light within the cell, since it is a very thin film solar cell. So the light trapping is also due to the texture of the upper layers here, where the multiple reflections from the facets of these texture aid also in keeping the light inside the cell, thus increasing the absorption and consequently the efficiency of the cell. The cells were delimited with using metallic shadow masks on very large substrate that were used to deposit the thin films. These substrates are 20 by 20 square centimeter substrate, and the area active of the cells that were delimited by these shadow masks is about 1 by 1 square centimeter. Okay, so this slide here gives you the deposition condition parameters that we use to deposit the various thin films, mainly the intrinsic hydrogenated amorphous silicon, the N-type hydrogenated amorphous silicon, and also the hydrogenated amorphous silicon carbide thin films were all deposited by plasma-enhanced chemical vapor deposition, PECVD. This technique allows both simultaneous deposition and doping of the films by just changing the gas mixture that we used during the deposition. In addition, this technique also enables to make either amorphous silicon or microcrystalline and nanocrystalline silicon. It's just changing the composition of the precursor gases within the deposition chamber. And mainly the dilution ratio, which is the ratio of the hydrogen to silane. This ratio governs the structure of the deposited silicon thin films, in addition to the substrate temperature also, and of course, the deposition at the RF power of the plasma. Also, the aluminum back contact is deposited by radio frequency sputtering, and the deposition parameters are shown in this table for both the 3 amorphous silicon layers and also the metal. For the P-type hydrogenated amorphous silicon carbide, we used a mixture of silane with a flow rate of about 16 standard cubic centimeters per minute, hydrogen with a flow rate of about 280 standard cubic centimeters per minute, in addition, of course, to methane to form the silicon carbide and diboran here to dope, P-type dope the films. For the intrinsic amorphous silicon or hydrogenated amorphous silicon, we used mainly a mixture of silane and also hydrogen to form the film. Okay, for the N-type, as you can see in the silane and hydrogen gases, we also used phosphine for the N-type doping. And of course, the deposition rates are rather slow using this technique. They are on the order of 1.3 nanometers per second for the P-type layer, 0.334 for the intrinsic layer, and also 2.1 nanometers per second for the N-type layer, and 1.61 for the aluminum. As you can see, aluminum is deposited by RF sputtering under an argon atmosphere at a power of about 3,000 watts. And the other films, the plasma power is about 15 to 30 watts, which is rather small power. In addition to temperature, the deposition temperature or the substrate temperature is rather low also. It's on the order of 180 to 190 degrees C. Okay, so then I'll just now present some of the results that were obtained on these films using Raman spectroscopy. As you can see in this figure here, the Raman spectra of the 3 films, either the intrinsic, N-type, and P-type films, are dominated by this transverse optical mode, vibration mode of the amorphous network of amorphous silicon. In addition, we can also see and observe some of the peaks here that are due to the transverse acoustic and also the longitudinal optical mode. In addition, of course, to some overtones of these peaks. That means harmonics of these peaks. How did we conclude that the films are amorphous? By analyzing this transverse optical peak, and by deconvoluting this peak, we observed that it's only made of one peak that is centered at around 480 centimeter minus 1, which is characteristic of amorphous silicon, hydrogenated amorphous silicon. No peak that is characteristic of crystalline silicon or microcrystalline silicon or nanocrystalline silicon that usually appears around 520 centimeter minus 1 is observed, which suggests that the films are deposited under these conditions that are mentioned above are all amorphous in nature. This is a bird's eye view of the films, of one of the film, the intrinsic layer that was deposited on an underlying fluorine doped tin oxide or FTO coated glass. You can see the F2O layer, and above it you can see the intrinsic hydrogenated amorphous silica layer, and as you can see, the surface of the layer is also textured. And as I mentioned, since the underlying FTO layer is also textured. Okay. As I mentioned before, this texture enables light trapping within the cell and favors the absorption within the cell, or enhances it rather. Okay, so we also did some ellipsometric measurement in the films in order to determine the optical properties, their optical properties, mainly the optical band gap, the thickness, in addition to the refractive index, and so on. So in this figure, we can see, shows the ellipsometric parameters, the phase angle, and also the amplitude parameter here as a function of the photon energy. The experimental points, the experimental results are indicated by points, and the fits that were obtained using the widely used Tocque-Lorentz dispersion model is also presented in this figure. This is the line here. And as you can see, that the fitting results in very good agreement with the experimental results, yielding an optical band gap for the three films that is shown in this row. For the intrinsic hydrogenated amorphous silicon, we obtained an optical gap of 1.7, while for the N-type hydrogenated amorphous silicon, it's about 1.62, and for the P-type, of course, deposited under the conditions that are mentioned, the optical back is 1.7 electron volts. As you can see, it's a little bit higher than that of the intrinsic layer because of the presence of carbon within the film. Okay, I also here presented some of the values that were obtained from literature. As you can see, the band gap here varies between 1.74 and 1.6 for the intrinsic amorphous silicon. And as you know, this parameter or the characteristic of the films generally depend on the deposition conditions, and mainly the flow rates of the various precursor gases, the temperature of the substrate, the RF and the RF power, of course, and also the pressure within the deposition chamber. There are other parameters of the models. Also, they agree with the experimental ones that were determined, obtained from the literature. The row here also, this gives the refractive index and the extinction coefficient at a particular wavelength. As you can see, the refractive index of the films are around 4.1 for the hydrogenated amorphous silicon films, and 3.39 for the P-type hydrogenated amorphous silicon carbide film. We also performed some optical measurements, transmittance measurements, in order to obtain the absorption coefficient of the films. And this is a typical representation using the Tocque's law of the absorption coefficient, which shows the existence of a straight line portion, and the extrapolation of this straight line enabled us to determine the optical band gap of the film. In this case, for this particular film, the optical band gap is around 1.78 electron volts, which is rather close to the values that are obtained by from the spectroscopic ellipsometry measurements. So these are complementary techniques that were used to determine some of the optical parameters of our layers. Now I'm going to switch to the solar cells again, and the parameters of the solar cells that were obtained Again, as you can see in this figure, I just remind you of the structure of the cell. It consists of an FTO substrate, coated glass substrate, covered with a P-type layer, okay, of hydrogenated amorphous silicon carbide of about 12 nanometers thick, followed by an intrinsic amorphous silicon or hydrogenated amorphous silicon, 260 nanometers thick, and then again with an N-type hydrogenated amorphous silicon and the aluminum back refractor. So the intrinsic layer is the photoactive or layer where the photo generation of the carriers takes place, and then these layers are what we call carrier selective layers, which enable only the transport one of the type of carriers, either the holes in the P-type or the electrons in the N-type layer. Again, the aluminum here acts as both a back contact of the cell, anomic back contact, and also as a reflector, which aids in trapping, light trapping, as I mentioned, within the cell. This is a typical current voltage versus voltage characteristic of the cells that were measured. I saw here two cells, but the best cell here that we have obtained so far shows an efficiency of about 8.83% with an open circuit voltage of 0.86 volts and a short circuit current of 15.6 milliamps per square centimeter, and also a fill factor of about 66%. Just for comparison, I also included in this table here the best efficiency cells obtained in the literature in this family of solar cells, and the record efficiency in this family of cells is about 10.3%. And as you can see, we are not that far. The difference is only about 1.2%. In addition, of course, this is for a cell area of 1 square centimeter, and the open circuit voltage also is not that far from our value. However, the short circuit current is the short circuit current for our cell is a little bit small, and also the fill factor of our cell is also a bit smaller. The lower value of the short circuit current can be attributed, of course, to the fact that we used thinner films than what is usually used in the literature. Okay, so this can be increased by increasing the thickness of the absorbing layer. However, the fill factor, the fact that it is probably the small value of the fill factor is probably due to the resistive losses in our cells, as we can see in the following slide. So we used the characteristics, the current voltage characteristic of our cell to determine the shunt resistance, which is the inverse of the slope of this line at the short circuit conditions. And also we determined the series resistance of the cell, which is the inverse, the negative inverse of the slope of this line at the open circuit condition at VOC. And also we obtained a value of the shunt resistance, which is about 560 ohms for the best cell, and also a series resistance of about 6, which is about 7 ohm. This value of the series resistance is rather small for typical solar cells. And of course, it's a little bit high for typical solar cells, and this value may be due to the underlying sheet resistance of the FTO contact, or if the FTO coated glass substrate. So we have to improve those values in order to reduce the series resistance, in addition, of course, to the contact resistance, since we use also aluminum, and aluminum may present some interface oxides and so on that increase a little bit the series resistance. The shunt resistance, on the other hand, is due to current leakage across the cell, and this value is not is rather small. Normally it should be higher than that. This explains why the fill factor, which is the ratio of the area under the curve here of the cell to the area of this rectangle here, that is determined by the short circuit current and the open circuit voltage, is small than the reported values for the best of the record efficiency solar cells. Okay, in order to shed some more lights on this, we also perform some capacitance versus voltage measurements on the cells. As you can see here, the capacitance increase rather slowly or slightly in the reverse bias region as we decrease the reverse bias, and then in the forward bias the capacitance increases. And the increase in the capacitance is a function of the frequency of the modulating signal that is used for the measurement, of the AC signal that is used for the measurements. As you can see, as the signal frequency increases in this direction, the changes in the capacitance decreases. And this is probably an indication that there are some traps in the mid-gap of the amorphous silicon layer, which I find it difficult to follow the modulation or the modulating signal that is used in the measurements. Okay, we also did some modeling using the SCAPS when the software that is widely used for the modeling of thin film solar cells. And as you can see here at 25 kilohertz, the capacitance here increases slightly in the reverse bias, and then in the forward bias, the capacitance started to increase in accordance with what we saw. And you see the geometry, the capacitance of the depletion layer here is around 37 nanofarads. As we can see, this is in agreement with the dielectric capacitance of our solar cells, which is only due to the intrinsic layer. We also have conductance here, and the conductance follows the same behavior, increases with increasing forward bias. At 1 kilohertz, the increase in the capacitance is much higher, as we saw in the experimental data. In addition, also the conductance follows the same behavior here. These are the experimental values of the measurements of the conductance. As you can see, the conductance versus voltage is rather asymmetrical due to the rectifying nature of the IV characteristic of the cell, and also the changes of the conductance with bias, are decreased as the measurement frequency increases. As you can see, if you go from the top here to the lower curve, the changes in the conductance, become smaller in accordance also to the measurements in the capacitance. And this is maybe attributed to the existence of those mid-gap states, which are finding it difficult to respond to the modulating signal that is used for the measurement. This we can see more this clearly in the measurements that were performed using the capacitance as a function of frequency in this figure here. Where we present the capacitance of the device in the dark, of course, as a function of the measurement frequency. As you can see, the capacitance decreases and then stabilizes in a plateau, in a well-defined plateau, with a capacitance of about 37 nanofarads. Okay, and simple calculation of the capacitance of the intrinsic layer, what we call the geometric capacitance or the dielectric capacitance of the cell, is in good agreement with this experimental value here. So this contribution is only the geometric capacitance or the capacitance of the intrinsic layer, and as the modulating signal frequency decreases, there is other contributions from probably the deep states within the bandgap of the material, because you know, as the frequency decreases, these states can follow you know, the modulating signal, you know, as the frequency increases. There is, of course, a turn on frequency, and this where these states start following the modulating signal, and this turn on frequency is a function, of course, of the applied bias. So this is figure is for the 0.5 volts forward bias, and the green one here is for 0.25 volts, and the blue one here is for the unbiased solar cell. And as you can see, this turn on frequency is a function of the applied bias. Again, below this frequency here, more and more mid-gap states or deep states within the band gap of the amorphous silicon or hydrogenated amorphous silicon are able to follow the signal or the AC modulation. Okay. We also presented the result in the form of Nyquist diagrams, and as you can see, the diagrams for various applied DC voltages for the cell. This is unbiased cell, and this is for a bias of 0.05 forward bias. As you can see, this diagram here is dominated by a single circle, okay, which is attributed to a single resistance in parallel with a capacitor, which are attributed to the resistance and the capacitance of the junction. And as you can see, this resistance here, which is given by the diameter here of the circle, varies with the applied voltage. Okay, so it nearly it decreased, in fact, with the applied forward bias. It decreased from about 600, or let's say 600 kilo ohms, or 0.6 mega ohms to about 8 kilo ohms here. Okay. This is due to the fact that we forward bias this junction, reducing, in fact, its resistance, and also the capacitance, as we can see in the previous curves, you know, also will increase in the forward bias. In fact, we will do some more modeling of these curves using, you know, more than one resistance and capacitance in parallel elements, you know, to get some more to account, you know, for the capacitance of the various interfaces within the cell, and this will be done in the future work. So, in conclusion, we were able to deposit successfully hydrogenated amorphous silicon thin films, and we also fabricated some single junction solar cells based on these films, which showed promising results. Our final objective, in fact, is not to optimize the PIN single junction solar cells, because these works have already been done, but we want to embark in the fabrication of heterojunctions, which are more promising and which yield more, which present rather higher efficiencies, compared to a single junction PIN solar cell. Okay, so with this, before I end, I would like to thank ISyDMA and Green Energy Park in Greer, where the cells were made by Kautar Belghiti Alawi, who is a PhD student, and also Aida Al-Alewi, who is also a PhD student. And I would also like to thank Shayma Nasser Abulula for the impedance spectroscopy measurements. And of course, I would like to thank the Center d'Analyse et de Caractérisation of the Qadi Iyad University for allowing us to use all the equipments, to do the various measurements. With this,